Okie dokie, everyone. We're going to take a look at page 72's homework and see how we did. All right, so firstly, we have a ball being thrown up into the air, and the question is what happens to the ball's velocity while it's in the air? Well, first, it's going to decrease, and it's going to then reach a zero velocity when it reaches its maximum altitude. Its acceleration is going to be negative 9.8 the entire time that it's in the air. It doesn't matter whether it's just before it hits the ground, doesn't matter where it's in the air. It's going to be negative 9.8 the entire time that it's in the air. The velocity is going to decrease on the way up, hit zero at its maximum height, and then it will increase on the way down. The acceleration is never zero while the football or while the ball is in the air. It will never be zero. The velocity will decrease because of that acceleration. It will stop because of that negative 9.8 acceleration, and then it will increase because of that. And you can see here I'm saying it doesn't matter whether you call it negative or positive. That means it's just a question of whether you're calling down negative or down positive. So let's not do 38. It's basically the same. Let's do 39. Similar. You throw a bouquet of flowers up into the air. Very exciting. That's a pretty nice bouquet if I do say so myself, and I do. All right. So the question is will the value for the bouquet's displacement be the same no matter where you place the origin? You can see I've placed the origin here where we're throwing it from. It's going to be the same motion. It's going to go up to the ceiling and back down, whether I put it where you throw it from or whether I put the origin on the ceiling. We can also see that the velocity is going to decrease, right? Here's some slow motion of the bouquet moving up. It's going to decrease. That velocity vector was decreasing. And the acceleration, okay, of the bouquet is going to be the same everywhere, just like in whatever that was, number 36. Okay, the object, I wrote it out here. I can read it to you because, that's what we do. The object will travel from the hand to the ceiling no matter where we measure from, i.e. where we put the origin. Our zero. All right, same as origin. Okay, so it doesn't matter. Same motion. All right, so here we go. We're going to drop a wrench. Okay, so a worker dropped the wrench off the building. It fell down. You could tell it was falling because of the whistling sound. And then here we are. So what are some things that we know about a situation like that? Well, because the wrench is dropped, that means it has a 0 meter per second initial velocity. It is dropped, so it is starting from rest. So it's going to speed up as it falls down as a result of the acceleration due to gravity, which is 9.8 meters per second squared. Now, as always, we've stuck with the convention that everything down is negative and everything up is positive. So I can draw this in here and I can say, well, up is positive, down is negative. This has some implications, of course, but we'll get to that maybe later. All right, so the acceleration is negative 9.8. Well, what about the displacement? Well, just like with the bouquet problem, we are now starting our zero right here. This is our zero for our axis. So if I were to draw my sort of y-axis thing here, I don't know if you can see that, it's right on the line. Here's my y-axis. This is where my zero is, right from where the wrench is dropped, right from the top of the building, which means this is the positive quadrant and this, okay, is the negative quadrant. Because of that, that means that 80 meters that it falls is all in that negative quadrant, which means it ends up 80 meters below where it started from. So its displacement is equal to negative 80 meters, not just 80 meters. 80 meters would be somewhere up here, way above him. Okay, so we gotta consider that. All right, so then what else? What are we looking for? What is the velocity that the wrench strikes the ground with? So some final velocity. No, the velocity the wrench strikes the ground with is not zero. We're looking for this velocity right as it's hitting the ground, not after it's bounced around and then eventually come to rest, right? You know that when you get hit by something, somebody drops something on you, it's not at rest when it hits you, right? Doesn't have a velocity of zero. Yes, there's going to be some interaction between the wrench and the ground that will eventually stop it, but that's not what we're talking about here. We are seeing with what speed does it hit the ground with. Okay, so just like always, because we've written in this particular way, we can look down this column right there, and we can use this to help us find an equation. The equation that we want to use now as a result of this is VF squared is equal to VI squared plus 2AD. Just want to call your attention to a couple of things here as we start to substitute in. Firstly, it needs to be noticed that these are both negative signs. I don't know. It's hard to underline a negative sign, right? I'll circle them, right? So that's a negative sign, and that's a negative sign. Okay? If this wasn't the case, right, for this particular problem, you know, after we're done squaring 0 and realizing it's 0 and feeling silly for putting that into our calculator, we would see that, well, of course, right here we have a negative times a negative, so it's a positive, so we would get, 1,568, okay, is what we would get here for our next line. But if one of these was positive, let's say that we made that displacement positive, well, then we would end up with a negative 1,568, and that is problematic when we are trying to solve for VF and we take the square root of both sides. That cannot be a negative, okay, which means that this has to remain as a negative. You can never just say, well, I'll just make it a positive. It has to have a reason. Mathematically, it must have a reason for it to be positive, otherwise it won't work. Okay, so now we just need to take the square root of this, which is going to be somewhere in the 39 range. Let me just do that real quick. Okay, so VF is going to be about 39.6 meters per second. Remember, whenever we take a square root, there's that plus or minus that hangs out in front of it. Because the wrench is traveling down, we choose the negative, because the wrench is certainly not going to hit the ground while it's traveling up. You can see it's pointing in the downward direction. This is the negative direction, so we need to choose this as a negative direction right here as well, and that's our answer. Okay, so number 41 is a bit of a tricky problem. We're going to throw a ball up into the air, and then we're going to catch it. So it deals with the up and the down. The issue is what information we're given and how we are going to make sense of it. So let's go over it here. At time 0, we throw it up into the air. It reaches its highest point. Okay, then it falls back down. Now, the time that is given to us is the time it takes for it to return back to the person's hands, meaning the total time, the time up and down. Now we know some things about these types of problems. We know that time up equals time down, that the velocity that you throw it with is the same as the velocity you catch it with, that the acceleration is always negative 9.8, and that the displacement up is going to be equal to the displacement down. So we can look at this a couple of ways. So here's the first way. We can start by looking at it, by placing our 0, by calling our initial when we throw it up. All right, so that's we start at the throw and we end at the top. So our initial is going to be when you throw it, and our final is going to be when it reaches its highest point. Okay, so that's that initial velocity is up, and then it's going to reach that highest point. So let's take a look at how we would formulate our variables in that sense. So we would say our initial velocity is we don't know. It's what we're looking for. But because we're calling the top, it's the end of when we're looking at it, all right, that velocity is 0. Doesn't mean the trip is over. It just means that's when we're stopping considering it. But the time there is not 3.56 seconds. Okay, that is only halfway through the trip. So that is half the time of the trip. So we divide those two things, and that will be the time it takes to get from the bottom, the lowest point, up to the highest point. And that's the tricky part. The most common mistake here is that people use that 3.56 as the time, but that is the time it takes to get back down. If you are using a 0 for a velocity, you are not talking about the total trip of an up and down motion. Okay? It is only 0 at the highest point. It is not 0 anywhere else along the trip. All right, let's take a look at option 2. Option 2 is just as valid, and in this case, we can start looking at it when the ball is already at its highest point. So it's like we close our eyes for the trip up, we open them when the ball is at the highest point, and then we watch it fall. All right, so just like before, we're only looking at half the trip. This is not the only way to do it. These are just two ways to do it. All right. So if we are again only looking at half the trip, the only thing that really changes here is that my initial is now at the highest point and my final is now at the lowest point, which makes my initial velocity now 0. See? It's always 0 at the top. So if you're starting to look at it at the top, that's where it's 0. The final velocity would be the thing that we don't know. You might say to yourself, well, I'm not looking for the final velocity. I'm looking for the velocity it's thrown at. But the velocity it's thrown is the same as the velocity it's caught. And it is important that, again, we use that half time because we are only looking at half the trip. Time up equals time down. Add the two together, you get the total time. If you're given the total time, you need to divide it in half if you're going to be looking at the half trip. So the equation looks very similar. It's VF is equal to VI plus AT is the equation we're going to use here. But instead we're solving for the final velocity. We get the same value. We just end up with that negative sign out in front. But again, the velocity it's thrown is equal in magnitude to the velocity that it's caught. All right, so we could have done it as a trip up and trip down and used that total time. But the advantage of doing it this way is because we have this second question of how high did the ball rise? All right, how high did the ball rise is half of the trip. It reaches its highest point halfway through. So knowing information about the start and end isn't necessarily as useful. We need something about that half time, more than likely. It's not the only way, but now that we have these velocities that we know occur on the trip up and on the trip down, and we have the half time that we know that time occurs from the lowest point to the highest point and from the highest point to the lowest point, which is where that maximum displacement occurs, we can use that. So in this first example, we're going to start at the bottom and go to the top. So starting at the lowest point and ending at the highest point with that initial positive velocity going up and that final velocity being 0 at the highest point. This means that it is changing, the velocity is changing from 17.4 meters per second at the bottom to 0 meters per second at the top as a result of that acceleration of negative 9.8. It travels that distance d over that time period. Okay, so your initial is at the bottom, the acceleration causes a change in velocity, you cover distance d over that period of time. That leads us to the equation of VF squared is equal to VI squared plus 2AD. Okay, so the main part of this is actually that initial setup, right, where we're determining our variables. After that, the rest of this just becomes math. All right, so we square the 17. Again, do not forget to square stuff. Okay, when we use this method, we need to make sure we subtract to the other side and that we divide by the negative, and we will get a positive displacement upward, okay, of 15.5 meters. This is the vertical distance the object covers as it's changing from 17.4 meters per second to 0 meters per second. Okay, you can see I didn't use the time here, sort of on purpose. We have this information, and so we can use it. I'm avoiding the issue of whether or not I should be using the half time or the whole time. Obviously, I already got over that hurdle, but in the future, if you know something about velocities, it could be advantageous to you. Okay, from top to bottom, looks almost identical. The difference here being that our final velocity is now the negative portion at the bottom, okay, and then our initial velocity is that 0 at the highest point. I miss a negative sign there, but I square it, so I get that 304. Subtract to the other side, and I get my negative 15.5. All right, so the same answer but negative because we are traveling a distance down. All right, the ball is falling down, so we're putting our 0 where the ball is starting at the highest point and ending at the bottom for that negative displacement.